Okay, I think we'll go ahead and get started. Hello, everyone. My name is Saman Razavi. On behalf of the convening team, Jeff McDonald, and myself, we'd like to welcome you to the 7th seminar of this year's seminar series on breakthroughs in water security research. Next week, we will have Sue Bentley from Penn State University. As always, we'd like to thank Howard Tweeter, the Canada Excellence Research Chair and the Director of the Global Institute for Water Security for underwriting this seminar series. This week, it's a pleasure to welcome Jim Hall to Saskatoon. Jim is a professor of climate and environmental risk and the director of the Environmental Change Institute at the School of Geography and the Environment in the University of Oxford. He previously held academic positions in Newcastle University and the University of Bristol before moving to the University of Oxford in 2011. Jim is a thought leader in the risk-based planning and management of water resources. He's made significant contributions to the development of theoretical basis for methods of flood and water scarcity risk assessment that are now widely being used in the UK and internationally. His third book, titled The Future of National Infrastructure, a System of Systems Approach, has recently been published. Seems quite interesting. And also, out of his countless publications, I'd like to mention that Jim has been a contributing author to the Nobel Prize-winning fourth assessment report of the IPCC, Intergovernmental Panel on Climate Change, a reference that many of us have used. Jim has served the community in different initiatives. Just to name a few, he leads the UK Infrastructure Transitions Research Consortium, and he is also a past co-chair of the Global Water Partnership. Not surprisingly, his outstanding work has brought him a lot of awards and recognition. To name a few, Jim has been awarded the George Stephen Medal and the Robert Alfred Karl Prize of the Institution of Civil Engineers in the UK. He is also a fellow of Royal Academy of Engineering. It's indeed a great pleasure to have Jim with us today. Jim, the floor is yours.
Thanks very much indeed for that introduction, Samar. It's a great pleasure to be here and to learn something of the very exciting work on water security that is taking place here in this university. What I'm going to talk about is going to be a combination of substance and methodology. As you've heard from that introduction, I've spent much of my academic career working on methodology, and that's what I quite like, so you're going to get a bit of that. But I'm going to begin by putting things in context in terms of sketching out some of the challenges that we're facing with respect to water security, and in particular, water scarcity in the UK at the moment. The UK is obviously a bit of a different place to Canada, but there will be a number of, I think, similarities as well as differences in what I'm going to talk about. And in fact, some of the issues I'm facing are very, very general globally, and much of the methodology that I'm working on is transferable into those different global contexts. Before I go any further, let me acknowledge two of many people who I've worked with on this, but Eduardo Borgameo, who's a former doctoral student of mine now at the World Bank, and Mohamed Mortazavi, who is a postdoctoral researcher in my group, and many of the results that you'll see come from those two people. So, first of all, to set the scene, that there is a sense in water resources in the UK that nothing much has happened for the last 20 years or so. That the water industry was privatized in the early 1980s. a series of 11 monopolies were created, and a regulatory setup, both an economic and an environmental regulator, was put into place to regulate those monopolies. And at the start of that privatization process, the main motivation was to keep those companies in business and keep the finances flowing. And then since then, there have been a number of different phases of change, one of which was around water quality, and the role of European regulations in encouraging cleanup by the water industry of point sources. Now we're entering a different phase where, having for a while thought that security of supply was not something we needed to worry about, recognizing that actually security of water supplies is a very big threat potentially facing the UK. In 2012, that going into that Olympic year in London, there'd been more than a year of very low rainfall, and was the prospect of severe water shortages in London during the Olympics. Then, as some of you may recall, it started raining in April, and for the remainder of the year there was record-breaking rain for the rest of the year, so that shortage never materialized. But in a sense, that was a wake-up call. And there are a number of factors which are pointing in that direction. One of which is climate change. This is just 4 of a dozen or so regional model simulations which are indicating the effect of climate change on summer flows. You probably can't see the scale precisely, but red is percentage reductions in summer flows. You can also see that there's a great deal of variation across those climate change simulations, and that's something I'll come back to in a moment. So we don't know exactly what direction climate change is going to push those flows in, but we do know that climate change represents a major source of uncertainty and potentially increasing variability. This is where the climate change signal does become a bit more obvious. So here we're looking on this axis at precipitation, this at evapotranspiration. The black dots here are historic data. The grey dots are simulations from our latest set of climate simulations, UK CP09 simulations, and this is for the baseline. So for the baseline, observation simulations more or less in the right place. That's a good thing. Looking into the future, this is now 2040s. Precipitation, total precipitation per year, not really much change on that axis. But because of the temperature signal, evapotranspiration going up. So at least we can say this, that we don't really know exactly what's going to happen with respect to precipitation, but the temperature signal means that there's a increasing pressure on water resource systems because of the increase in evaporation and transpiration. The next driver is what's going on with population. Here we are with a population of 63 million at the moment. This is a central projection which gets us to about 75 million in the 2080s. And there's a pretty wide range in the Office for National Statistics scenarios around that. And if you look at where that population might be located, that's in this lower panel. These are increases. Some of these are the lower total growth scenarios. These are the higher total growth scenarios. But in all of those scenarios, most of that population is going in the south and the east of the country. One might question whether that is necessarily desirable, but it's very difficult actually to work on a population scenario which doesn't see the southeast of the country being the main location of population increase. And why is that so significant? Well, because the southeast of the country is also the driest part of the country, and also because water resources in the UK are predominantly used for public water supply. So agriculture is, for the most part, rain-fed. In total, agricultural abstractions amount to 3 or 4% of all abstractions. Water and energy are the big abstractors. So changing population accompanied with per capita demand means that demand for water is going to be going up. And the third big factor here is the recognition that what we have been withdrawing in many contexts is unsustainable. So the amount of water being taken out of the environment is more than appropriate to sustain good ecological status in those water bodies. And this is analysis, again, by the Environment Agency, and the red patches here is where water is not available for licensing. So there can be no more licensing of water in those water bodies because they're already over-abstracted. So we have these convergent pressures. What do they all add up to? Combination of climate change, population increase, and unsustainable abstractions. Depends on how you do the numbers, but it points to supply-demand balances which are going in the wrong direction. So again, red is bad here. You don't need to look too carefully at the numbers. But large areas of the country, including the southeast, but not restricted to the southeast, which have prospective supply-demand deficits going into the future. What are we going to do about that? The Water UK has just done quite a large study around this, and there's a sense that you need to do everything, and you need to start on the demand side for a number of reasons. One is that there are lots of relatively low-cost demand-side interventions which haven't been adopted, and so it would be relatively low cost to adopt them. Secondly, because I think if you endeavor to propose things on the supply side without doing as best you can on the demand side, then there will be a lot of very legitimate pressure not to do that. And similarly, in relation to leakage, so leakage rates from the public water supply are around 22% at the moment of water is lost due to leakage. We have lots of very old pipes, some of them laid in the Victorian era. Digging up streets and replacing those pipes is a very, very costly and disruptive business. But again, it's hard to propose new things on the supply side if you haven't done more in relation to leakage. The third area is around abstraction reform, and this is a very major topic around how can we change the license arrangements for a whole range of users so that we're restoring sustainable abstractions in catchments which are over-abstracted, and we're more able to adapt. The system is more flexible, more able to cope with change going into the future. And then once you've done all of that, there still needs to be thinking about new strategic water resources. So new and enhanced surface and groundwater resources, groundwater recharge, new and enlarged reservoirs are on the agenda, lots more thinking about water transfers, so interbasin transfers between different river basins, desalination. We already have one desalination plant in London, and more desalination plants are planned. Probably a great deal more direct effluent reuse, so taking effluent from wastewater treatment works and putting it back into the supply system, and doubtless some combination of all of those things. Then the next thing is, well, does this all add up? and this is where we need to start doing the numbers. And the simplest thing one can do with the numbers is looking at these effects of population change on public water supplies. So these are the blue bars here. This is how much demand could go up by, and then how much could that demand increase be offset by. The purple bar here is an ambitious target for leakage reduction. The green is demand reduction savings. And in low and central population scenarios, actually, if you're active enough on the demand side, you can probably cope with the increasing population. In the high population scenario, the two roughly balance one another out. But that's before you factor in the climate change effect and the reductions in abstraction, the so-called sustainability reductions, so the restoration program. And once you've factored those in, it looks as though more might be required on the supply side. And this is just one kind of depiction of the sorts of major infrastructures which are now being contemplated. These icons are roughly scaled in terms of the size of the resource, and you can see the legend here in terms of what those resources are. The biggest thing coming up is major effluent reuse in London and the southeast, more desalination plants along the south coast, raising of reservoirs in Wales, potential new reservoirs in central England and Lincolnshire, and this network of transfers, and you can see the direction of all of these transfers. This isn't a national water grid, but it is catchment to catchment transfers which are gradually shifting water towards the southeast of the country. And that's the direction we're heading in to adapt to these changing pressures going into the future. So that's the kind of sketch of the problem we're dealing with. The question now is, well, given this kind of portfolio of things you could do, how do you decide what to do in the face of a wide range of possible uncertainties? And so this is where the methodological innovation comes in, and this is where the work we do in my group is seeking to contribute. And water resources planning, of course, has been around for a very long time, and the way in which the water utilities have conventionally done this is to come up with a projection of demand and a projection of how much water might be available for supply. That's what's shown in the graph above here as well. Apply some kind of uncertainty factor, which they refer to as the headroom, and then work out what the supply-demand balance is, and then use some kind of least cost optimization to put together a series of supply-side interventions to meet that supply-demand gap. That's what's been going on for a very long time, and it's the sort of approach which is used in plenty of countries worldwide. We think this approach is problematic for a number of reasons. And the way in which we've sought to recast this is in terms of not supply-demand balances, but what are actually the things that we're concerned about within this system? What are the risks? And how effective might different sets of interventions be in terms of reducing those risks? So this is the principle which we're trying to get taken up in practice. So how do we get away from thinking about abstract quantities like deployable output or yield, and think about actual observable things like water shortages which affect people and the environment? And so we're seeking to reframe the whole decision problem in terms of the probability and consequences of those shortages. So the principles that we're working to is quantifying risks of system failure based on metrics of the frequency, severity, duration of restrictions of water use for people and the environment at present and in the future, incorporating uncertainties. And then the way in which we then proceed is to take lots of different possible combinations of interventions and see how they might reduce those risks and put together portfolios of combinations which demonstrably are cost-effective and efficient at reducing those risks to a tolerable level, while satisfying other requirements like the environment's requirement for water. And the other much more explicit part of this is recognition of the interplay between the main abstractor we have in mind here, abstractors for public water supply, and all of the other abstractors within the system, so users for energy, for industry, for agriculture, and the environment's requirement for water. And so we're seeking to explore the trade-offs between those different users. Central to that is an explicit acknowledgement of the role of uncertainties. And the methodologies we've developed are based as far as possible on probabilistic treatment of uncertainties, including climate uncertainties, where we can obtain probabilistic scenarios of the scale of those climate uncertainties. And then alongside that, we recognize there are a bunch of things which are very challenging to quantify in probabilistic terms, and in that context we use scenarios. So we use scenarios for population growth, scenarios for land use change, scenarios for how much society might choose to reduce its abstractions from the environment in order to restore the aquatic environment. So those two slides just have set out the principles of the way in which we're now approaching this problem. I'm now going to say a little bit more about the methodology for how we're actually doing this. And the first thing is how we're driving all of this thing with climate scenarios, and specifically with large ensembles of synthetic streamflow records. This one actually is not streamflow, it's evapotranspiration, PET, because at least with that one sees some kind of climate change signal in it. If I'd showed you streamflows, it would have just been a kind of cloud of points going off in more or less the same direction. This one here shows in the baseline period, we have just, we're looking just at climatic variability. These future simulations are conditioned on results from a large perturbed physics ensemble of climate model runs. And so each of these time series represents a different realization of a climate model. And so by looking between these, we can see the difference, which is basically boils down to the climate model uncertainty. One could try and disentangle the emissions uncertainty in that. In fact, you wouldn't see very much at all in terms of the emissions uncertainty. Most of this variability is down to the climate model uncertainty. There's something else which I'll just mention in passing here. This piece of work here is based on stochastic weather generators. Another piece of work we have in my group, which we're just about to release, is based on very large ensembles of regional climate model simulations using a citizen science initiative called Weather at Home, which farms out regional climate models to people's PCs. That's led by my colleague Miles Allen and Freddie Otto. So from that, we're getting very, very large numbers of regional, tens of thousands of regional model runs for the UK. And so we're going to, in future, be running this directly off regional climate model outputs rather than stochastic weather generators. The advantage of that is that this weather generator here is a single site weather generator, so one doesn't have spatial coherence, whereas the regional model outputs, if we're looking at interbasin transfers, the spatial coherence is very, very important. So that's the first step. The next step is to do some rainfall runoff modeling. No rocket science in what we're doing there. There are lots of established hydrological models we can use in the UK. We are being careful to pay attention to the uncertainties in those hydrological models, in particular in the low flows. And then the next step is using those flow series as an input to simulations of the water resource system. So this type of system model, this is a system model for the Thames Basin, has a series of flow points from the hydrological model, every abstraction point and all of the abstraction rules. So this is the way in which the rules are determined in the Thames Basin. They're determined seasonally. They're determined according to how much water there is in storage, and they're determined about the level of flow, by the level of flow in the river. And those abstraction rules then determine how much water the water company can take from the river. And we then simulate all of the allocation within that basin. This model is now being extended to all of Britain. And by doing those simulations with the synthetic flow series, we can then count the number of times that abstractions are restricted, so the number of times and the duration that water users will have some level of shortage. The water company has certain levels of service for those amounts of shortage. So the lowest levels of shortage here involve bans on temporary uses, bans on water for gardening. The highest level of shortage involves rotor cuts to users, standpipes in the streets, so people being cut off from the water supply. So this is really very major and disruptive level of shortage which one would have for the public water supply. And you can see the water company's targets for these different levels of shortage, including the so-called never for a level 4. Now, we know that in probabilistic terms there's no such thing as never, and in fact a lot of what this work is about is saying, well, actually there is a genuine risk of this type of restriction. Let's try and be a bit more explicit about what that risk is and seek to manage it in a more proportionate way, given the severity of that risk. So what these simulations give us is for each one of those flow series, we can count the number of shortages or estimate the annual frequency of shortages. So we do long simulations, so we can estimate these frequencies quite well. Is the annual frequency 0.05? Is it 0.1? Or is it less? So these are low frequency events. This is when the system is not having shortages at all often. You'll recall that I had many repeat realizations of those flow series, each one doing a slightly different thing in the future. And so as we resample and do this lots and lots of times over, we get some histogram of what the estimate of the frequency of shortage is. And this is the histogram in the 2020s. This is the histogram in the 2050s. And you can see how, as we go into that future climate change, as we impose the population increases on top of it, the things are moving towards there being more frequent shortages. And if we're interested at this level 3 target, 1 in 20 years, 0.05, come the 2050s, the tail of this distribution is being pushed out beyond that target. And what we actually do is integrate over this tail of the distribution. That's the probability of the company failing to meet its target. And that becomes one of our main metrics of the performance of the system. What's the probability that we'll fail to meet this target? And this is another way of recasting that. If we look again at this level 3 restriction, so here we've got these different levels, level 1, level 2, level 3, level 4. This is the worst type of event for the water company. Let's look at this one here. This is our target, 0.05 annual frequency. This is the cumulative distribution from that histogram. So I've converted the histogram into a cumulative. Right now, we're way back on the safe side of this line. As we go into the 2030s and 2050s, the upper tail of that distribution begins to push past our target. And that probability I was talking about is the distance between where this curve crosses the target and 1. So it's about 0.01 is that probability of failure at a level 3 level come the 2050s. And what we can then do on top of that is impose some different scenarios. So here we're now using that probability, annual probability of exceeding the frequency of level 3 shortages. That was the 0.01 in 2050 I just showed you. This line here shows no population growth. This shows some different population growth. This one here shows a combination of population growth and a doubling of the environmental flow requirements. So we're able to take less water out of the environment. That's the effect of that on this probability of system failure. And really, I mean, as far as the water company is concerned, anything beyond this kind of zone down here is intolerable as far as they're concerned. They're prepared to tolerate a very small probability of failing to meet their target, but not much beyond that. So what this is showing is what the different effect of those drivers on the performance of this system going into the future. And one can then begin to look at what are the alternative management options. The black here is a no option one. Ignore all the squiggles around here. That's basically just sampling errors. If we did the demand management and the leakage reduction, then actually we could get that down, probability down to a more tolerable level, though it would still begin to tick up come the 2040s, 2050s. If we somehow get some more resource from somewhere, this is an effluent reuse plant, then one can knock that probability of failure down to a very low level. And the way in which we've begun to think about this is in terms of this notion of adaptive pathways. So what are the combinations of different interventions you might put together in order to manage this risk? And we've come up with this kind of dashboard type presentation of that, which shows, well, what's the climate hazard indicator? This is, here we've got annual flows and the mean down here. So that the flow indicator is very gently going down, nothing much happening there. What's the exposure indicator? This is the population. That's going up, but with some pretty wide uncertainty ranges. What are the alternative adaptations you might do? And here we're looking at how can you stack up a number of different adaptations, some efficiency technologies, leakage reduction, universal metering, some innovative pricing mechanisms, and then nonetheless, with even all of those, this risk-based metric is still ticking upwards. So again, we say, right, come the 2050s, this becomes intolerably high. We have to invest here in the water reuse plant that I mentioned previously. That gets the risk down again, but this population driver here is still pushing it up. And so it looks as though in the latter part of the century, further intervention is going to be needed. But this type of kind of dashboard setup provides, this is just one possible adaptive pathway, but it provides a way of visualizing what are the pressures on this system, how might we respond to them, how effective is that response going to be. That's still just looking at one possible set of responses. It's a portfolio. It involves some demand-side stuff and some supply-side stuff, but it's still just one possibility. Of course, there's a multitude of possibilities in terms of the way in which we could put all of those things together. And so one has to go through a series of filters to narrow down what those options are. Some of that depends on filtering out the ones which are not feasible in engineering terms or fail initial environmental assessments. The bit I'm interested in is how we identify options down here, so at the last stages in the process. We start by saying, right, well, what's the tolerable risk within this system? And we'll look at all of the sets of options which help us to achieve that tolerable risk. And then we do some optimization to find, well, what's the set of least cost options which might satisfy that tolerable risk? But we're not just going to go for one least cost option, so do the pure optimization. Because when we look at the results of those optimization, we find that they're very, very sensitive to the uncertainties, to the assumptions. They're not at all robust. So we look at a set of possible near least cost options, and then we, in that set, explore their sensitivity with respect to multiple criteria. So how are these doing both in cost terms, but in reliability terms, environmental terms, and so on and so on. And so this gives a kind of overview of the optimization setup that we adopt to do that. I don't think I'm going to go into that, but just to show you some of the ways in which we're presenting the results of it. This is back to the same way in which I was talking about this problem a moment ago. These are our levels of service. This is the probability of failing to meet that level of service. This is a cost axis here. So these are the highest cost. These are the lowest cost portfolios of interventions through time. And each one of these lines represents one of those portfolios. So the first thing this tells you is that in order to get the risk down, it costs you. So there's a risk-cost trade-off here. That's because it's red at the bottom and blue at the top here. The higher risk ones are the lower cost. The lower risk ones are the higher cost. So there's clearly a trade-off here. The second thing is that these lines here are all pretty flat. So actually it doesn't matter too much which one of these targets you aim to achieve, because if you're meeting, say, your level 3 target, you're probably meeting the level 4 and the level 2 target as well. But the chances of meeting the level 1 target are a bit lower. Now, actually, when you then interact with the decision makers in the water company, they're much less worried about this target anyway. If there are a few hose pipe bans, that's not the end of the world. What they really worry about is what's going on up here. So this helps to illustrate those types of trade-offs. Another way you can look at it, this says pretty much the same kind of story. This is the cost axis here. These are these different levels of restriction. The lowest cost solution has by far the highest risk. The highest cost solution has the lowest risk, and we can see that there are some trade-offs going through this system. These types of parallel contour plots are very useful for visualizing these types of multi-attribute trade-offs. And then what we've done is said, right, well, suppose our tolerable target is that the failure frequency has to be less than 0.01, so we filter out everything else which is below that. That then becomes our kind of final set of possible solutions which we're going to look at a bit more carefully. And the way in which we did that, I'm sorry that this is not very easy to see, but this tries to tell a story of what these sets of policies are. So we've got a whole series of different things we're doing in this system. We're building reservoirs and sewage treatment works. We've got, we're trying to incentivize users to use less water, and so on and so on. So just think about each of these as being one of a number of possible things we might do on the supply side and the demand side. And each row in this kind of tableau here represents an investment pathway. So you can see that each row contains a few of these dots, which means that we've got to do a number of different things in this system. And then the color of the dots, which probably you can't see very well, represents the year in which we have to do it. So the blue dots are the ones we do early, the yellow dots are the ones we do late. And so there are lots of alternative adaptation pathways we could adopt. This here, you're looking at about 40 different adaptation pathways here. What you can see is that of those adaptation pathways, there are a sum which where a given option is included lots of times. This one here is a big reuse plant, 150 megalitres a day reuse plant. This one is a new treatment works. So those interventions seem to pop up a lot of the time. Those are the sorts of things you probably are going to expect that you're going to have to do, whereas some of these other ones are hardly ever selected as being part of your adaptation pathway. And then we look across from each of these pathways to look at what the cost and the risk associated with it is. So, how are we doing for... How long have I got? Oh, okay, right. So that, I should have asked that question beforehand. Anyway, we're nearly there. That piece there was talking about how we plan these adaptation pathways. The last thing I want to talk about is now looking at testing the robustness of this system to very severe droughts. So droughts which might not even appear within our simulations, because we want to stress test the system to understand how might it perform in the worst possible conditions. This is actually some historic analysis of droughts. This is the proportion of the area of Britain under drought. And you can pick up some of the more severe droughts that we've had in the past, 1976 drought being possibly the worst one. In fact, it goes through 1975 there and into 1976. So severe droughts happen, and we know from the paleo record that much worse droughts than this have happened in the past. What I'm interested in is stress testing the system to see how it responds to those droughts. And the things I've been talking about, the frequency of water restrictions as being an important risk metric, but actually when you look at the consequences of water shortages, the duration is equally as important. So you need to look at both severity and duration in order to understand how bad a drought is. So this is what we're looking at here. If we have some kind of low throw threshold, we can define the duration of the drought and the deficit, which would be the integral under that line there. We have a flow series like this. And the sort of thing we're actually interested in is sequences of dry months and indeed dry years, one after the other. So we're interested in the month-to-month and year-to-year dependence of low flow conditions. And you can see, if we look at month-to-month scatter plots like this, that there is some dependence in it. But it depends on where in the year you are and where in the record you are. What we've done to do these stress tests is to start with the observed stream flow and then model the temporal dependence from month to month and year to year using copulas to represent the dependence structure, and then to do some bootstrapping, modifying the temporal dependence to come up with sequences, and including sequences as extreme as this one here, which have very, very long periods of drought, achieved simply by resampling the observed record. And we use things like that in the stress test. And so what this enables us to do is, if we do this bootstrapping, we can actually fill up a space with loads of synthetic droughts of different duration up here and deficit down here. These red dots here are all of the observed droughts. And here you can see, right, so in this kind of set of stress tests, we're really pushing the envelope out. There's a lower bound to this relationship because this is all developed by resampling the observed record. So there are certain conditions in this space which you can only get to by going outside the observed record. But just by resampling the observed record, we can generate very many possible drought sequences. And then across that space of drought sequences, we can calculate what this, how frequently failures might occur. So using this same probability of failure metric. This, in a sense, is a kind of sensitivity analysis. How sensitive is our system to droughts of different duration and frequency? In this one here, red is bad, so this is very high probability of failure. And we can see that as you push out from this envelope, both of observations and of climate scenarios, you begin to get out into the space where the system becomes very sensitive to these severe droughts. It's interesting that actually the kind of the folklore in southern England is that the worst conditions occur when you have prolonged droughts. Actually, this plot here suggests that you have to have that combination both of duration and severe deficit in order for the conditions to be threatening for the system. It's not just enough to have a long drought. You now need a long drought with a very significant deficit in order to stress test the system. The question which which you kind of immediately get asked if you look at a plot like this is, well, this is where the observations, the climate scenarios are, so how bad could this get? So is it really plausible to look right up there? And the answer is no, it's probably not very plausible to go right up there. These are very, very unlikely conditions. Let's see if we can do some kind of robustness analysis starting in the conditions which we know we observe quite frequently, and let's kind of explore the sensitivity of this space as we go further and further out from these everyday conditions. And I'm going to do that by basically fitting a probability density to, again, using a copula to this cloud of dots here, and extend that density plot further and further out, and then look at the performance of the system over that space. I'll skip over that one and just kind of go straight to the results. So here you can see I've fitted a density plot. And what I'm interested in is, as I go into less and less likely conditions, or as I push out over these contours, what's the worst thing that could happen? So what's the reddest color I get within any given contour area? And that is used as a test of the robustness of my system to this increasingly severe set of possibilities which I'm exploring. And that's what I'm plotting here. And I can use that robustness analysis to compare different water resource management options. So this is in a sense, how far out am I going in those contour plots? These are the really, really unlikely things out here. This is the more everyday stuff down here. This is my failure probability metric. And if I do nothing, this is the way in which the performance of my system tails off as I go further and further from the everyday conditions into this really bad stress test future. If I do some different interventions, here we're looking at water transfers, here we're looking at demand and leakage reduction, I can increase the robustness of my system, so I have to go further along this axis before bad stuff starts happening. These types of analysis are most interesting when the robustness response of your options looks very different. Some of these are very steep, some of them are very flat. In fact, in this one, these curves are all pretty much the same shape, which isn't very interesting, unfortunately. But this is an instance of how you can do this type of robustness testing, looking at much more extreme droughts than have been observed in the past. So that's taken a skip through some methodology which helps to implement in practice this approach to risk-based decision-making, which I've promoted, which in turn is helping us to address some of these water resources challenges which England, but also many other places around the world, is facing in the future. And the approach which we're promoting involves a lot of simulation, as you've seen, and that's important because it enables us to sample all of the variability and also to explore possible uncertainties going into the future. And the good news is that this is all very, very feasible now. So we can do large numbers of simulations on clusters and do this type of very extensive analysis to build our confidence about the robustness of the system. We're using scenarios to deal with those uncertainties which we struggle to quantify in probabilistic terms, in particular because they're dependent upon policy decisions which haven't yet happened. And we're using multi-objective optimization not to try and identify an optimal solution, but much more to explore the trade-offs and present those trade-offs to decision makers so they can understand the implications of the choices that they're making. And then we're layering on top of that robustness analysis to do the stress testing of the system, to look at how it's going to fail, how it's going to perform in the most extreme droughts. And this is all becoming extremely relevant. This takes us back to where I started, is that some big decisions are going to happen in England and in many other parts of the world. In England, this will happen in the coming decade. We've got a whole series of policy reforms in the pipeline and some very major investments. And so what I've been presented is very much motivated to make sure that we can make better choices in the future than sometimes we have done in the past. So thanks a lot for your attention. I'd be very happy to answer any questions you have. Here are some papers.
Thanks very much, Jim. Yeah, what you described, I certainly think it's the best way to move forward, really. So we have some time for questions. So I may go with the first one. So the way you described the sequential approach from climate change projection studies to hydrologic modeling, water management, optimization, policy making, I wonder what you think about the feedback between water management and hydrology. would that be helpful to couple hydrology and water management together, as there might be some feedback on the land surface, for example, as a result of human intervention?
Yeah, so first one comment on that question is, yeah, in some sense the methodology we presented is feed forward, and it goes from climate to hydrology to water resource system to impacts and then decisions. But where I got to at the end was much more from a kind of robustness analysis type perspective, so where you start with the options, with the decision, and then you're looking at the robustness of that decision to possible changes in the hydrological conditions. So, and I think you need to have both of those approaches, both the feed forwards and the feedback in your decision making. But I think with specifically what you were hinting at there was, should we be doing more coupled modeling of the hydrology with the water resource system model? And I agree that that's the case. I mean, we already have the return flows, so the discharges from the treatment works go back into the river. So in that sense, there is some coupling, but there are lots of innovations coming up around groundwater recharge, around effluent reuse, around different upstream, downstream trade-offs, where actually you get to a point where you can't analyze that in an uncoupled way, and you do need a fully coupled system model. We haven't got there yet, but I think you're right that is the direction of travel.
Thanks. Questions? Andrew.
Hi. Kind of a general question. I'm not sure if I'm really clear in my mind about the relationship between uncertainty and risk. And is it the case that high uncertainty would dampen the risk? Or are these completely separate concepts? Because, I mean, uncertainty is a statement of how confident you are about something happening, and risk is a statement of the probability of it happening. So how do these two concepts sort of come together?
Yeah, that's a very good question, and there's a particular framing here. So there is no definitive answer to that. So let me just explain how we're approaching it, which is we're using probability to represent the natural variability within the system. So the all of that stochastic stuff is determined by stochastic processes, and so that's all represented in probabilistic terms. And then there's another, and from that stochastic analysis, one can do things like analyze frequencies of system failure, and you'll recognize that was one of the main metrics that I'm using. So you need that probabilistic layer in order to come up with that reliability metric. And then what we're saying is that the system reliability is itself uncertain because of a whole number of other things which we're unsure about, like population growth, like the sustainability reductions, and indeed like the climate model uncertainties. And some of those uncertainties we're representing in scenario terms, but the climate model uncertainties, we're using probabilistic estimates from the perturbed physics ensemble. And so we end up with a probability distribution on a reliability metric, a failure frequency. And so the climate uncertainty is represented with a probability distribution over a frequency. that's the way in which we've structured it, but might be other ways of doing it. I think what one can say in general is that in these instances, be it water resources or flooding, where I've done a lot of work, you have to have that underlying probabilistic analysis to estimate risk, and then on top of that, you acknowledge that your risk estimate is always going to be uncertain for a number of different reasons.
We have time for one more question. Amin?
Hi, thank you for the presentation. This is a question I have been carrying along for some time. I've been asking myself and some experts like you. So when it comes, especially that eventually we're interested to some risk-based decision making, and given those kind of very broad ranges of uncertainties that come from different sources like climate scenarios or even like hydrologic models, you know, would it be possible to do the same type of analysis with very simple stochastic methods like traditional stochastic methods without needing to use complex climate models or hydrologic models, and possibly end up with the same decision at the end?
I'm quite attracted by the analytical solutions to some of these stochastic problems, which I think is what you're kind of hinting at. But I think in practice, when we start looking at real systems, one ends up needing to do simulation modeling in order to capture the complexity of those systems. So, for example, the sorts of things I was referring to in response to Samar's question, if you've got a complex water allocation system with feedbacks between the water allocation and the hydrology, I think you have to simulate that. There isn't going to be a closed-form solution to it. With respect to the climatic effect, I think you can go a long way with doing some quite simple things with the climate, simply because the climate models don't warrant doing anything more sophisticated. So just looking at changes in means and variance and seasonality might be all that's really warranted. And so you could then take that forwards into a more simple stochastic analysis. But if you've got complex spatial systems which are operated in complex ways, I think you have to simulate them.
Right. I guess we're at a good point to stop. We're walking to Alexander's for a drink, so everybody's welcome to join us, and we can have a more informal discussion there. Thank you very much all for coming, and thank you very much, Jim, for coming. It was great to have you here.